Stress strain curve is our topic today. So to draw a stress strain curve, we will take a metal wire of a particular length. For example, let us choose a wire of length 1 meter. So we will choose a wire of length 1 meter and we will hang it vertically with some weight, with some initial weight. Okay. And we will fit a scale also attached with that. Now gradually we will add weights. So initially we will add small weights. We can see it will elongate. Then we will just remove the weight. We will check whether it is regaining the shape. If it is completely regaining the shape, what we will say? It is elastic. Okay. So for each weight, we will measure the elongation. We will calculate stress and strain. And we will plot a graph between stress and strain. Here you can see that from the point O to A, we are getting a straight line. What is the meaning of that? Corresponding to this value of stress, this is the maximum strain corresponding to this value, and strain and stress are directly proportional from O to A. We can say it is obeying Hooke's law. So from the region O to A, stress is proportional to strain. We will say it is elastic. Means if you remove the stress, this value of stress which we have applied, when we remove the stress, it will completely regain the shape. Okay. Further we increase the stress, we will increase the load, it will again elongate. So suppose we apply a stress up to this value, Sy. Okay, so we will increase the stress from here to here. Then we can see that stress is not directly proportional to strain. Not directly proportional. From O to A, we had a proportionality. When we increase stress, strain also correspondingly increasing. But here from A to B, we cannot see any proportionality, but it is regaining the shape. When you remove the stress of this value, it will regain the shape. So we can say it is elastic, but it is not proportional. So it is not proportionately undergoing strain. Stress and strain not directly proportional from A to B. So the point A is known as proportional limit. Up to point A, there is proportional. Afterwards, not proportional. So it is called proportional limit. Now this point is called yield point or elastic limit. This is the point where after the point B, it is not elastic. That's why it is called a elastic limit or yield point. Okay. So up to the point B, when you remove the added weight, it is regaining the shape. Actually, if it was 1 meter length, up to this value, we have applied a stress. For example, 5 kilogram we had. When you remove the entire 5 kilogram, it is regaining the length of 1 meters. It had 1 meter initially. We apply 5 kilogram corresponding to this value stress. If you remove the 5 kilogram, it is again getting 1 meter length. It is regaining the shape. That's why I am calling it elastic. Okay. Now again we add continuously the weight. We can see that up to a point C. When you remove the weight, it will slightly regain the shape, not completely. Means 5 kilogram we have added, it has completely regained the length. You are adding 2 more further weight, means total 7 kilogram. When you remove the 2 kilograms, it is not getting 1 meter length. It may be having 1 meter, 1 millimeter length. 1 meter and 1 millimeter. It is retaining some length. Then here onwards, what we call, it is regaining some length, retaining some length. Okay, it is not completely regaining the shape. We will call it is plastic. It has started to become plastic. Okay, and this region, this strain is called a permanent set. It is permanently set. Means now its length is not 1 meter. It is permanently set as 1 meter, suppose 1 millimeter. It is a permanent length. So this strain is corresponding to permanent set. Okay, so it is regaining a certain length. Even though when you remove the entire weight, it will have some 1 millimeter length or 2 millimeter length. Okay, now further we increase the weight, increase the stress. What happens is, for small stress, the strain is very large. So you can see the stress is small, but the strain is very large. So up to a point, up to a particular stress, we can increase the weight. And this stress is called yield ultimate tensile strength. That is a maximum stress. Thereafter, you can see, if you just increase the weight beyond this point, you can see the wire goes on thinning. It becomes thin and ultimately breaks. So this is the fracture point. So if we slightly increase the weight beyond the point, it will break. So the point is called a fracture point. Okay. So from O to B, it is elastic. Then B to D, we can say it will be plastic region. Small stress, there will be larger strain. A to B, stress not directly proportional to strain. Not directly proportional, but it is even it is elastic. Here O to A, it is stress proportional to strain and is elastic. Now what is yield strength? Yield strength means the stress corresponding to the yield point. Means yield point is corresponding to elastic limit. This point is B is elastic limit or known as the yield point. The stress corresponding to the yield point is called the yield stress. It is called yield strength or yield stress. And this is the maximum stress we can apply without breaking. After that, if you apply slightly more weight than this stress, what will happen? It will break. That's a point called fracture point. This is ultimate tensile strength. So we have two stress values, SY and SU. SY is called yield strength and SU is called ultimate tensile strength. So if you apply a weight slightly more, even if you are just remove the weight after applying the maximum weight, if you decrease the weight even though, it will start to elongate. This will be elongation, then ultimately it will break. Okay, this point is called a fracture point. Now, based on stress strain curve, we can classify materials. For example, we have two graphs like this. This is one graph for a material A, and this is another graph for a material B. We have stress strain graph. Strain and stress, the similar graph. Here also stress and strain. You have two materials, A and B. Suppose the shape is like this. Okay, these are the points. And for this graph, these are the points. This is point B, point D, and this is point E. Here this is a D and this is E. See, in these two graphs, in graph A, you can see the points D and E are very close. Here there is large distance between D and E. This means that before breaking, it stretches to a large length. Here, if you just increase the weight or even though you decrease, these 2 points are very close. Means this will not stretch too much. If you increase the weight more than this D value, the value corresponding to D, it will break. Such materials are called, having this kind of a graph are called brittle materials. They will break very easily. And they are called ductile materials. Ductile and brittle materials. There are another type of material called, we can say, elastomers. This is a shape of elastomers graph. Here we have a strain and a stress along y-axis. So we can see for small stress there is large strain. Even the stress is small, the strain value is large. Example of such materials. These materials are called elastomers. We can see many examples like rubber is an elastomer. Then tissue of aorta. These are examples of elastomer. For elastomers, for small stress, strain will be very large. So these are the category of materials based on stress strain curve. Here importantly you have to note these points: yield stress or yield strength, ultimate tensile strength or ultimate tensile stress, that you have to note down these points. This A is called a proportional limit, B is called elastic limit or yield point. Okay, E is called a fracture point. Now there is an important question that can be asked. Somebody will ask you, which is more elastic? Either it is steel or rubber. And for rubber, we can see that for small stress, to get large strain, we need only small stress. But for steel, to get that much strain, we need to apply larger stress. Okay, large stress, if we need to apply, there will be larger restoring stress developed. So there is larger restoring stress developed in the steel wire for a particle elongation. For example, for 5 millimeter elongation, I'll give an example. For 5 millimeter elongation, I'll use rubber and steel. Okay, the rubber is requiring only 2 Pascal stress. Here steel will require more. It may be requiring around 10 Pascal stress. If 10 Pascal is the stress, what will be the restoring stress? Restoring stress will be equal to 10 Pascal. So it requires more restoring stress. It will develop more restoring stress. It will develop only less restoring stress. So somebody is asking you which is more elastic. Definitely we can say based on the value, we can say which is more elastic. Steel is more elastic. So more elastic. Which is more elastic? Steel is more elastic, and this will be less elastic. So this will classify based on which value, the value either with the value of Young's modulus or with the value of stress we can say. So it requires more stress, or restoring stress will be larger for steel. Okay, that's why steel is more elastic than rubber. Okay, I hope that you have understood. Thank you.